Good morning, everyone. This video we are going to cover section 6C, normal distribution. The normal distribution is a symmetric, bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution. Its variation is characterized by the standard deviation of the distribution. So this is the definition for normal distribution. It mentions mean, median, mode. Three measures of central of a distribution. We have this covered in previous videos. For normal distribution, all those three measure of centers are equal to each other. Okay, yeah, so this is one feature about the normal distribution. For normal distribution, the mean, median, and mode are the same in the middle, in the peak. Normal distribution is a single peak distribution. It's bell-shaped. It's like this. It's like this one. Okay, this is the peak. This is the peak. The corresponding x value here is the center. Mean, median, and mode are all equal to each other. Mode, median, and mean are all equal to each other. It is symmetric, single peak, and bell-shaped. Bell-shaped. If you look at it from the left to the right, you see it's going up, reach the maximum, and then going down. Normal distribution has two tails, left tail and a right tail. This diagram is a histogram for a normal distribution. You can tell from the histogram, the normal distribution, the distribution is symmetric, roughly, and single peak, two tails, right? Bell-shaped. Yeah. So this histogram is a roughly normally distributed. The data it represents. The histogram on the right-hand side, on this one, population density, frequency. Obviously, this one is not a normal distribution, right? It's not a symmetric, it's not a bell-shaped. And what kind of data set is normally distributed or roughly normally distributed? A data set satisfying the following criteria is likely to have a nearly normal distribution. We have the following four standards or criteria. Number one, most data values are clustered near the mean, giving the distribution a well-defined single peak. Number two, data values are spread evenly around the mean, making the distribution symmetric. Number three, larger deviations from the mean are increasingly rare, producing the tapering tails of the distribution. Number four, individual data values result from a combination of many different factors. Those factors, none of those factors are dominating. So the individual data kind of like a combination of many tiny, small factors. None of them are dominating. But they all contribute to the individual data value or the variable, the random variable. That kind of random variable is likely to be normally distributed. For example, people's height, weight, blood pressure, pulse rate, salary, food size, shoe size, and so on. They are combinations of many small, tiny factors. And for example, I think we talked about this before. People's height. Most of people, their height is about average, cluster around the mean. Only small portion very tall, small portion very low, very short. Or salary. Most of people, their salary is about the mean, right? Maybe some less, some more, but around the mean. Very small portion, they have a very high salary, and a very small portion people, they have a very low salary. And now we know the center, mean, mode, median. The center is the peak. And for the variation, we learned the measurement of variation in previous video. We know standard deviation is one way to measure the variation of a distribution. So if the variation of a normal distribution is big, then you would see the bell shape kind of like this, very flat and low. You know what I'm saying? If the deviation, if the standard deviation, the variation is smaller, then you would see a relative thinner bell-shaped curve. All right, does that make sense? So the center, the mean, median, and the mode determine the center. Where is the center? The center not necessarily at 0, okay, by the way. It could be positive, could be negative, any real number. And the variation or the standard deviation determines the shape of the normal distribution. This one has a bigger variation. This one has a smaller variation. Example 1. Which of the following variables would you expect to have a normal or nearly normal distribution? Here we mention variable. Random variable is a basic and important concept in statistics. Random variable. Let's say we consider a population. Many values, right? So we can bring in a random variable, x. Let x represent all the values in the data set or in the population. The value of the random variable depends on the subjects in the population. Okay? So which of the following variable might be normally distributed? A. Scores on a very easy test. If the test is well designed, the scores should have a normal distribution. But this one, the test is easy. Easy means what? Means most of people, they get a higher score. You know what I'm saying? So what kind of distribution that is? Skew to the right or skew to the left? Skew to the right, okay? Let me draw it. It's an easy test. So I'm not going to write a vertical asymptote, vertical scale, because the mean is not really 0. The mean might be 80 or 85, right? So it's supposed to be like skew to the left. I might misspoke that earlier. So if the test is easy, most of people, they got a higher score, right? Less people get a lower score. So that make the distribution skew to the left. Skew to the left for easy test. Part B, shoe size. This is a typo, shoe size. Shoe sizes of a random sample of adult women. What do you think? Yeah, that is normally distributed, okay? That is normally distributed. Shoe size is like kind of like people's height or weight, blood pressure, pulse rate. Those variables are normally distributed. Most of people, their shoe size are around the average. Very small portion of people have very big size shoes or feet, and very small portion of people have small feet. Let's see. Yeah, solution. We can read the answer in words. Tests have a maximum score of 100% that limits the size of the data values. If a test is very easy, the mean will be high and many scores will be near the maximum. The few lower scores can be spread out well below the mean. We therefore expect the distribution of scores to be left skewed and not normal. Skewed to the left, right? Yeah, and you can think about that. If the test is hard, then the distribution is gonna be skewed to the right. Part B, shoe size depends on foot length, which is a human trait determined by many genetic and environmental factors. We therefore expect women's shoe size to cluster near a mean and become less common farther from the mean, giving the distribution the bell shape of a normal distribution. Right? So I believe you might have a good understanding already about the concept of normal distribution. It's pretty simple. Think about the name normal. It's everywhere. Normal distribution is everywhere. It's normal. So the next up, a very important theorem. The name of the theorem is called the 68, 95, 99.7 rule. Sometimes you see the book call this theorem empirical rule. Just different names for the same thing. Different names for the same thing. So let me show you the content of this rule. Firstly, this rule only applies normal distribution. If the data set is not normally or roughly normally distributed, then the rule does not apply. Okay? Again, 68, 95, 99.7 rule only applies normal distribution, or the data set is roughly normally distributed. It tells us if a data set is normally distributed or roughly normally distributed, then about 68%, actually it's 68.3, we rounded it down. About the 68% values in the data set fall within one standard deviation away from the mean. This is the mean, right? The peak. Sigma here. Do you guys remember those notations? X bar, mu, sigma, S. Do you guys remember that? X bar, sample mean, mu, population mean, S, sample standard deviation, sigma, population standard deviation. When we talk about distribution, here, when we talk about random variable here represents the whole population. So we use a population standard deviation, sigma. 68 means if the population is normally distributed, then about 68% of the values in the population fall within one standard deviation away from the mean. Is about here, okay? Yeah, about 68% values in the population gather around the mean, only one standard deviation away from the mean. 95, if the And if the population is normally distributed, then about 95% of the values in the population fall within 2 standard deviations away from the mean. Okay? 95% is like a majority, very big portion. And 99.7 in a population which is normally distributed, about 99.7% values, that kind of like almost all, right? 99.7% values fall within 3 standard deviations away from the mean. Okay? So actually we have, you can see from my graph here, do you see this pink region and this blue region? Do you see that? Huh? So because 99.7%, so if we subtract 99.7% from 100%, 100% all the values fall on the real number line, of course, right? From negative infinity to positive infinity. We know 99.7% fall within 3 standard deviations away from the mean, and it means only 0.3% outside the 3 standard deviation. Because the normal distribution is normal, I mean symmetric, because the normal distribution is symmetric, we have about 0.15% on the right tail, in the right tail, and another 0.15% in the left tail. The yellow part, those are the 99.7%. Almost all the values in the population which is normally distributed fall within this range. Okay? And 0.15%, those are very rare, R-A-R-E, and this 0.15% also very rare. Does that make sense? Yeah, that's the content of this rule. The 3 numbers kind of give you the information about the theorem. Yeah, let's say it again. If we have a population, and the population is normally distributed, then about 68% of the values in the population fall within 1 standard deviation away from the mean. About 95% values in the population fall within 2 standard deviations away from the mean. And about 99.7% of values in the population fall within 3 standard deviations from the mean. Okay? And if we have a data set, it's kind of like a sample. And the sample is from a normally distributed population. Then we would say the values in the sample is roughly, at least roughly standard, normally distributed. Then we would have similar similar result. But here we use the sample mean. Sample mean is going to be in the middle, and S would be the sample standard deviation. It's the same thing, okay? Just different notation. If you see the data set as a population, and that's a mu and a sigma. If you see the data set as a sample, then you use the sample mean X bar and the sample standard deviation S. Am I clear about the content of this theorem? It's a very important fact about normal distribution. If you are business if you are business major, you might heard about a theory. It's called the 6 sigma theory. You can Wikipedia about the information. Yeah, it's pretty interesting. It's business, but it's based on this fact. Okay, another thing. We have many normal distribution, right? Depends on the value of the mean and the value of the standard deviation. Among those normal distributions, there is one type of normal distribution is very special. It is called standard normal distribution. Standard normal distribution. So I'm going to explain standard normal distribution maybe right here. Standard normal distribution. Yeah, among all the normal distributions, there's one type of normal distribution very special and important. It's called a standard normal distribution. Then what kind of normal distribution is a standard normal distribution? Simple. If the normal distribution, we use n to represent the normal distribution. You might not see this notation on the book because that's my own notation, but it's very convenient to apply. Normal distribution, if the center or the mean of the normal distribution happens to be 0, origin, and the standard deviation of the normal distribution happen to be 1. That's kind of special, right? Because those numbers are so convenient. Then the normal distribution is called a standard normal distribution. The notation for standard normal distribution is n of 0, 1. All right, the first component or the first parameter means mean, mu, population mean mu, which is 0. Second parameter here is standard deviation sigma, which is 1 for standard normal distribution. Am I clear about that? Standard normal distribution is a normal distribution with mean equals 0, standard deviation equals 1. It's special. Okay? All right. Then if a normal distribution is not a standard, then we call it non-standard. Non-standard. Does that make sense? Non-standard. Yeah, if the normal distribution is not a standard, then we call it non-standard normal distribution. Let's say we have a population X. The random variable X here represents the population. We know that the population is normally distributed with mean mu, standard deviation sigma. Yes, normal distribution has 2 important parameters. In a way, we can say the normal distribution is determined by the mean and the standard deviation. Yeah, those are 2 parameters. If we standardize the random variable X, how do we standardize it? If you recall from the previous video, we have a z-score formula. This is very similar with that. If we subtract mean mu from X and all over the standard deviation sigma, we would have a different variable z, right? And z would be standard normally distributed. I want you please remember this fact. Very important. Earlier we have covered the concept of standard normal distribution. Then for non-standard normal distribution, we are able to standardize it. Standardize it is a verb. Standardize. We are able to standardize it. How? We subtract mu from X and all over sigma. Mu is the population mean. Sigma is the population standard deviation. Then of course we would have a different variable, right? Let's say z. And z would be standard normally distributed. The mean of z would be 0. The standard deviation of z would be 1. It's a very interesting fact. Okay? Yeah, so you can actually see this as a z-score. In essence, is the same with the z-score we have talked about in previous videos. Okay? All right, so that is the empirical rule, the theorem, and what is non-standard deviation, non-standard normal distribution, and what is standard normal distribution. So now let's look at this table. Okay, let's look at this. Oh, you know what? Yeah, look at this curve. Look at this curve. This curve. Center is 0, origin. And standard deviation is 1. This curve is the Z curve. Sometimes we call it the Z curve. CURVE. Z curve is the density curve. Density curve of a standard normally distributed variable. Okay. The big Z, the variable, is a standard normally distributed with mean 0, sigma equals 1, and this is the Z curve, standard normal distribution curve. Standard normal distribution curve. Okay. One important feature about this curve is the area under the curve and above the x-axis is 1 or 100%. So if you look at the pink region, since the pink region is half of the region enclosed by the curve and the x-axis, so the pink region actually has area 50% or half. As I wrote here, the area of the region to the left of the origin is 50%. The origin happened to be the center of the standard normal distribution. And now let's look at this table. This actually is a two-row table. You see 6 rows because it's like a term. So actually only have 2 rows, okay? The first row, z-score. Second row, percentile. Yeah, let's take time to really understand this table. Kind of very important, this table here. First row, z-score. Z-score actually is the value of the variable z, which is standard normally distributed. Or you could just understand z-score as the z-score we covered from previous video when we talk about relative standing, measure of relative standing. Okay, z-score is just like that. So that's the first row. You see the first row, z-score could be -3, -2, -1.5, and so on and so on. What if the z-score is a -0.8? Means what? Means the value that you concern, we use x, lowercase x, the value that you concern in a population. The z-score of that value is a -0.8. Means what? Means the value that you concern is below the average. And 0.8 standard deviation below the average. Okay, you see what I'm saying? So z-score, just simply understand it as the relative standing of the value you concern. We covered that in previous video. The second row is the corresponding percentile for your value. Okay? Yeah, of course, this table is only for normal distribution, not applied to other distribution. Okay? Yeah, this table only applies to normal distribution. What does that mean? For example, if the z-score of the value x, your value x, is a -0.8, from the table we know the corresponding percentile is 21.18. What does that mean? It means in a population, there are about 21.19. There's about 21.19% of the values below your score. Does that make sense? Okay, so if we look at here, if the z-score equals 0, what does that mean? Z-score equals 0 means the value that you concern. When we talk about z-score, we have to think about z-score of what? Z-score of a x-score, whatever the value you concern, okay? Suppose the score, the value that you concern is x, and the z-score of your value is 0. That means what? That means your value is right in the middle in a normal distribution. Does that make sense? Is right in the middle. Of course, then the percentile would be 50%. Half of the values in the population below your value, another half above your value. So the percentile is 50%. How's that? Yeah, we can keep going to explain more. Now let's say the value concerned is x again. But this time, the z-score of your value is 0.9 positive. That means your value is above the average in the population. How much above? 0.9 standard deviation above the average. And the corresponding percentile from the table is 81.59. Means there's about 81.59 people, or values in the population below your score. Yeah, if the score is kind of like a score of an exam, like a standard exam, then yes, about 81.59% of the people who participated in the exam has a lower score than you. Does that make sense? Yeah, one more. Now let's say this is your score x, and you compute your z-score. The z-score of your value happened to be 2, positive, so above average. And how much above? 2 standard deviation above. By the table, the corresponding percentile is 97.72%. That means in the population, about 97.72% values below your score. Then it gives you an idea where does your score stand in the population, right? Very top, on the top. Your score on the top in this case. Does that make any sense? Yeah, this is how do we understand this table. We're gonna use this table in the package. Now let's go over the package. Number 1. Alice took a standardized test. If 96% of the students scored below Alice, 2% had the same score, and 2% had a higher score. What percentile was Alice in? This problem tests your understanding about the percentile. We covered the percentile in previous video. Because there is about 96% of the students scored below Alice. Alice's score has a percentile 96%. 96. So we should choose B as in boy. 96%, 96th percentile. Okay, we consider how many percent of the values below your score. That is the percentile. I think it's clear enough. Number 2, assume a set of test scores is normally distributed with a mean 480 and a standard deviation 20. About what percentage of scores lies between 440 and 480. This is a good problem. We need to really take time to understand this problem. I need to find a space to write things. Yeah, I actually have those things written. How about you just look at it here? So here X is the population. X is normally distributed. X is all the scores for the test, for the standardized exam. It is normally distributed with mu center 480, standard deviation sigma 20. Okay? And we are looking for the percentage of scores lies between 440 and 480. So one way to think about it, so I'm going to use a different way to talk about this problem. Yeah, I do have my notes. I do have different methods in my notes, but I'm going to explain in a different way. So here we have two numbers, 440 and 480. How about let's talk about 440 first. Okay? Yeah, let's say your score now is 440. It is X, is an X score, okay? And now I want to find the Z score for your score. Yeah, how do we find the Z score for 440? Do you remember the formula? Z score equals X minus X bar over S, right? But here we have the population mean and the population standard deviation. It would be the same, okay? Just use it. So X is 440. Center is 480. Standard deviation is 20. By using this formula, we have the Z score of the score 440 is -2. You can do the math yourself. 440 minus 480 is -40. -40 divided by 20 is -2. Okay? So we know that 440 has a Z score -2. Okay? Let me write it here. Maybe let me highlight it. We know 440 has a Z score -2. And I just show you how to find the Z score. It's pretty straightforward. And now let's deal with 480. Yeah. Now let's deal with 480. .480 is a score in the population. We want to standardize it. So we subtract the mean from it and all over the standard deviation. 480 minus 480 over 20, we got a 0. Turns out the Z-score of 480 is 0. Okay? All right. So look at the table. The table gives us the corresponding percentile for the given Z-score. If Z-score is -2, where is it? -2. Here. If the Z-score is -2, the percentile is 2.28%. Did you see this graph? Do you see this diagram? You can zoom in. You can actually pause the video and zoom in. So the shaded yellow region is 2.28%. Because the Z-score of 440 is -2, then the corresponding percentile is 2.28, means 2.28% value is below 440. Below 440, okay? Yeah. So now we know about the 2.28% below 440. Below 440. And then let's think about 480. Because the Z-score of 480 is 0, we know 50% value is below the value. So look at this diagram, the yellow region and the blue region together, 50%. Okay? Yeah. So we have 2.28% values below 440, 50% below 480. Then how many percent between 440 and 480? Let me say it again. I believe you can figure it out. There is 2.28% below 440. There is 50%, 50% below 480. Then how many percent between 440 and 480? You use 50% minus 2.28%. You have, what is this? 47.72% between 440 and 480. Okay, so what should we choose? 47.72. Well, we would choose the closest one. B is the closest one, and you choose B. B as in boy. But the exact percentage is 47.72%. Let me repeat the solution for number 2 again, because this a little bit challenging. Okay, yeah, this one is a little bit challenging. Let's read the problem again. Assume a set of test scores is normally distributed so that's the reason we can use the table. Mean is 480, standard deviation is 20. We need to find how many percent of the scores in the population fall between 440 and 480. We deal with those two numbers, 440 and 480, separately. For 440, we firstly standardize it. We have its z-score equals -2. Then by the table, we know 2.28% scores below 440. And then we go ahead to standardize 480. We find the z-score for 480 is 0. That means there is 50%, 50%, scores below 480. Yeah, think about 2.28% below 440, 50% below 480. Then how many percent in the middle? How many percent between 440 and 480? You use 50% minus 2.28%. You have 47.72%. That's the percentage of scores lies between 440 and 480. Yeah, I think it's pretty clear. Just take your time, maybe repeat the video, figure it out. Number 3, assume a set of test scores is normally distributed with a mean 55 and a standard deviation 15. In what percentile is a score of 70? That's even easier. If you know number 2, you can easily do number 3. So now the score you concern is 70, 70. So X score is 70. We go ahead to standardize it. We find the z-score of 70 be 1. How did we do that? We subtract the sample mean 55 from 70 and all over the sample standard deviation 15. Yeah, we have 1. So the z-score of 70 is 1. Let's see. Z-score of the score is 1. Where is 1? 1 is here. By the table, if the z-score is 1, the corresponding percentile is 84.13%. Then you just choose 84.13%. Yeah, we don't have 13%, 0.13%, but you just choose C, right? You know that. just round it down. Isn't that easy? It's pretty easy, right? Number 2 and number 3 actually is the same type of a problem. Number 3 is pretty simple, straightforward. And number 2 is a little bit challenging. Number 4, suppose a data set has a mean 117, standard deviation 10. Find the z-score for a data value of 103. Easy. Number 4, simply just to find the z-score, right? The relative standing. Your x is 103 because you are finding the z-score for 103. So your score, your x is 103. Your mean x bar is 117 is given. Your standard deviation s is 10, which is given. Formula, you need to remember the formula, okay? Very simple, basic formula. Z equals x minus x bar all over s. And then you plug in everything. 103 minus 117 all over 10. You got the z-score is a negative 1.4. Is that doable? Number 4, simply just a straightforward application of this formula, z-score formula. Number 5, in what percentile is a data value that falls 0.6 standard deviation below the mean? How do we understand this sentence? The data value falls below the mean. So the z-score must be negative, right? Below, under the average, so it's a negative. How much under? 0.6 standard deviation below. So the z-score actually is a negative 0.6. This sentence actually tells you the z-score of your data value. The z-score is negative 0.6. And what's the corresponding percentile? Then you go back to this table. Negative 0.6. Percentile is 27.43. 27.43, so 27th percentile. Means about 27% scores is under the data value, which is not that good because means you're on the bottom, you're on the lower half. Number 6, about how many standard deviations above or below the mean is a data value in the 21st percentile. 21st percentile. So let's see. So this problem is given. In this problem, the percentile is given. The percentile of the data value is 21%. Go back to table, 21%. 21%. We don't really have 21%, but we have 21.19%. This one would be the closest percentile. So we're going to use this one. The percentile corresponds to the z-score equals negative 0.8. Let's go back. The corresponding z-score is negative 0.8. So the data value is below the average because it's negative, okay? How many below? 0.8 standard deviation below. 0.8 standard deviation below. Okay? If you still have some doubt or confusion from previous video about the relative standing, the z-score, I think this section would help you a lot to help you to understand z-score a lot better. Number 7, suppose in a company, 6,000 employees. In a company with 6,000 employees, the monthly salaries are normally distributed. The mean salary is $2,900 with a standard deviation 300. About how many of the employees earn more than $3,170 per month? Yeah, this is a challenging problem as well. So firstly, we know the population is normally distributed, has a standard deviation 2,900. Sorry, mean 2,900, standard deviation 300. Okay. So we have a special value here. We have a special value, 3170. So I want to go ahead to find the z-score of this number. I want to go ahead to find the z-score of this number. How do I find the z-score of this number? You're going to write it down, okay? You use 3170 minus 2900 and all over 300. You find the z-score for that value. Okay, you find the z-score for that value. I give you the time. Try use 3170 minus 2900 and all over 300. You tell me what's the z-score. Okay, the z-score is 0.9. And then go back to the table to see what's the corresponding percentile for 0.9. It is 81.59%, 81.59%, 81.59%. Okay, so that means what? Means that there's 81.59% employees, they pay less than that, percentile less than that. Then how many percent of employees pays equal or more than that? We use 100%, 100% minus 81.59%. We would have 18.41%. Means in a company, 18.41% employees pays more than $3,170 every month. And how many employees of that? In total, the company has 60,000 people. You multiply the total by the percent, you get the number of the parts, which is 1,105 people if you run it. All right, so this is a little bit a challenging problem. Let me repeat the process. We consider 3,170 this value. Okay, we consider $3,170 that value because that is important salary in the sample or in the population. We go ahead to standardize it to find its z-score. We use 3,170 minus the mean 2,900 and all over the standard deviation 300. We got the z-score equals 0.9. By the table, the corresponding percentile of that data value is 81.59%. Means there are 81.59% employees in a company pays less than that. Then if we use 100% minus 81.59%, we got 18.41%. Means there's 18.41% employees in the company pays more than that. And we use 18.41% multiplied by the total number of employees, 6,000. We got 1,105 people. Those many employees pays more than 3,170%. Okay, take your time. Take your time to understand this problem. Number 8. Prior to recentering in 2000, the mean of SAT verbal score was about 440. Assume that the standard deviation is 100. Find the z-score of a student who scored 390. This one is simple. X score 390. We need to standardize that to get the z-score. We know the formula here. All right? X is 390. X bar, the mean, is 440, is given. Read the problem. S is 100, is given. Read the problem. You plug in You do the math, you get a z-score. Number 9. After recentering in 1995, the mean SAT math score was about 500. Assume the standard deviation is 100. Find the percentile for a student who scored 420. We're going to do the same thing. This time, your X score is 420. Mean is 500 is given. Standard deviation 100 is given. Use this formula to find the z-score. You got a negative 0.8 and go back to the table to find the corresponding percentile. Number 10. The average person has an IQ 100. How do you understand that value? Average, that is the mean, mu, okay? Mu is 100. And the scores are normally distributed. Standard deviation 15 is given. What a percentage of people has IQ above 130? So 130 is an important value here, okay? So let's say your X is 130. That's the value we concern. We standardize X. We find the z-score for X. That's the formula for the z-score. We use 130 minus the mean, which is 100. All over the standard deviation 15. What do you have? You have 2. So the z-score of 130 is 2. And then you go back the percentile. Okay, let's see what's the percentile for 2. 97.72%, 97.72%, 97.72%. So 97.72% people IQ scores lower than 130. Now how many percent of? You tell me. If 97.72% below 130, how many above 130? You simply use 100% minus 97.72%. You have 2.28%, okay? 2.28%. Okay, so that's 6C, normal distribution. Repeat the video and understand the content. Thank you for watching.